Okay, this is chapter 16, and we're getting into optical flats and optical alignment. And we're kind of debating whether we should put this chapter in the course or not. But then I've decided you have to do it because it's very popular and well used in the real world. So it's good for you to get these foundations now. So we have already studied many measuring instruments from basic rule all the way to high amplification comparators. So this chapter is going to discuss the measuring instruments with the highest amplification. So the highest amplification instruments can measure all the way to 1 million power. And we're going to use light waves to do it. So the instruments measuring with light waves is it's not expensive, okay, and it's very familiar and then very rugged. So why do we use light? Is because they have a phenomenon, and that's a remarkable uh, phenomenon. And what we get from light is we get fringes. Okay, so these are the fringes patterns. Those are nothing but looks like the contour maps, okay? And we use that for micro measurements. And that's what light provides us. And we're now using this nature of light to do the measurement. Okay, so the fringes that you're seeing right now, it's going to make you dizzy a little bit if you look into it so long. So we use the fringes, okay, to measure or to do the measurement by using the light. And we call the instrument in which we use light to measure, we call that kind of instrument optical flat. So optical flat is nothing but just a transparent plate. And you have one face finished, and that one face finish is to near perfect flatness. It is really flat. And that's why we call this type of instrument optical flat. And this face onto another flat surface, we can then see the light bands called fringes, the one that I showed you in the previous slide. And in physics terms, scientific terms, we call these fringes interferences. Okay. So when we place this face, the flat face, onto another flat face, you're going to see the interferences of the light bands. Okay, and in common words, we call these interferences fringes. So these interferences, they correspond to the distance separating the two surfaces. Okay, that's how we do the measurement. The wavelength of light use, we know it, okay? We know all the wavelength of the light, so we definitely know that that's a known factor, so therefore the separation can be determined. So how do we do it? We count the fringes, okay? So by counting the fringes, we can be able to determine the distance of that separation between two surfaces. Okay, so metrology, there are 4 primary applications of optics. The very first one is magnification, making it bigger, yeah? So the visual enlargement of an object, so we can examine and measure it more precisely. Alignment. So using the light rays, we can establish references, and these references are nothing but, we already know them, your lines and your planes. Interferometer. Using the phenomenon of light, we can measure, okay, using the known wavelength of light as the absolute standard of length. So we're using the wavelength, okay, known wavelength as the standard. So that's what we do for our optic applications. The importance of standards here in optical measurement is that the measurement does not conform to the standard, okay, even if we have it. So that's true whenever we need to make a measurement to a subdivision of a unit that is smaller than error known to exist in the standard. So this kind of bulky to understand. What's trying to tell you right here is every time you make the measurement, okay, and if that measurement is made requiring a subdivision of the standard, and if that standard is smaller than the known error in the standard, okay, you're going to get a measurement out of confirmation to that standard, meaning like it's not going to conform to the standard. You will get something different. Again, especially for the measurement, okay, smaller than the known error. If you're doing the measurement smaller than the known error, okay, you're going to get a measurement out of confirmation to the standard. So here is your tolerance, required tolerance, and that's your part, okay. And here is your standard. See, the standard cannot provide a standard because the part, okay, is smaller than the standard error, okay. So standard error is nothing but the error in your standard. So that's this little part. But the part that you're trying to measure, you have your tolerance. When you compare this tolerance, okay, to the error in your standard, you see it's small. See, at that time, this kind of measurement is not going to conform to that standard. Okay, that's pretty easy for you to understand. Light waves as standards. So we don't use the light waves as our standard. So light was recognized again as a very useful standard by this guy. So Albert Michelson in 1852 to 1931. And another guy, Edward Morley, 1838 to 1923. So therefore, it was adopted as a practical standard. Okay, the advantage of using light as standards are the wavelength of light was more stable, okay, than any material that had been used in the construction of a standard. Because you can count on the nature, it doesn't really change, okay, it's just right there. At least for our time on this world. So the wavelength was so short that at the time, okay, so short that at the time at least, no one thought, okay, it will have to be divided into smaller units to increase the discrimination. Because the wavelength can go so short. So we can't make that amount of small units, okay, with mechanical devices here on our hand at all. So by using the nature naturally existing, okay, light, and the length of that is your wavelength, you can get, okay, to the shortest possible discrimination, okay. So humans are very intelligent, and you guys are more intelligent, okay, because I don't want to be so judgmental, but then I would say that, okay, it's in your genes, okay. You guys are smarter than many other species of human. Okay, anyway, so what I want to say is I don't want to talk about the race issue here. What I want to say is some of the genetics, they're very intelligent, that you should make effort because it's in your genes, okay. You're smart, you're intelligent, you're good, and this passing the exam should not be difficulty for you, okay. It should be easy for you, and all you have to do is just put effort into what you're trying to do. And one semester is really short, okay. It's only like 3.5 months, and I'm quite sure you can do it, okay. It's right in there in your genes. All right, the third one is The third advantage is because the light was relatively easy, okay, to reproduce. And we can reproduce light anywhere in the world. Quite easy, yeah? So therefore, using the light in the measurement is such an advantage. Okay, we're going to use optical flats to measure. White light. We already know white light, so that's from your physics. Is made up of a combination of color light. Okay, not all white light is going to use a color light in the same combination. Okay, they come in different combinations. So review your physics. So visible light is designated by color and spectrum. Okay, remember the spectrum lab that you can see the color inside. And that spectrum, okay, are wavelengths. And here are your review, your light wavelengths. So violet is going to start from 370, and then we can go all the way to 750 nanometers. Okay, so that's a short going longer right there. So these are our wavelengths. They are in nanometer. So nano is 10 to the power negative 9. So what more smaller, okay, what smaller discrimination can you have than this, okay? This is the smallest. We can even go smaller. If we go into different kinds of light, this is just a white light, by the way. So anyway, so the zone that we can play with is right in here from 370 to 750. Okay, so light wave is just a small part of electromagnetic spectrum, another physics review. Okay, so here is our electromagnetic spectrum, and you can be able to see our light right there. Okay, and here is our wavelengths. This go all the way. Okay, so you have 157. Pay attention to your decimals. Going all the way to red is longer, so 275. Yeah. So these are your nanos, okay? Okay, optical flat, you can coat it. So it can be coated. We use titanium oxide film to coat it. So why do we have to coat it? Because we want to reduce the amount of light lost by the reflection. We want the light. So we don't want to lose it. So we coat it so we won't lose it, okay? We usually lose the light by reflection. So the less light lost is in reflection, the clearer the fringes band, so we can do our measurement. Okay, set up for measurement. So to view an object properly through an optical flat, you got to be nearly perpendicular to the surface as possible, right, for the most accurate measurement. So the part is then ring to the flat for the measurement. So the part is not going to ring to flat if the surface is insufficiently flat. If the surface finish is insufficiently fine, or if the surfaces are improperly clean. So you have to clean the surfaces, the surface finish got to be fine, and the surface got to be flat sufficiently. So here you can see the smaller, okay, the smaller the angle, the more accurate the measurement is going to be. So here you're going to start with 5. So you got 1% error. When you go 30, you got 15.47% error. And when you go 45, you get 40.42% error. And when you go to 60, you get 100% error. Okay. So again, the smaller the angle, okay, the more accurate the measurement will be. And that's why we say the operator got to be nearly perpendicular for the most accurate measurement. Okay, so parallel separation plane concept, we use it to enhance the fringes. So in this concept, a set of planes that are all parallel to the working surface of the flat and one halfway lean apart. If we have that, they're going to give us the dark fringes at their intersection with the part. So the intersections of these planes and the part. So what this concept gives us is the dark fringes line is so important in our measurement. Okay, so therefore the number of fringes represent the separation between the surfaces in units of 1/2 wavelengths. We can get cosine error, okay, but they're in micrometers. So that's like a billionth of an inch. So here, these are the lines. We're just imagining these lines right there, okay? And they're 1/2 wave apart. It's just the distance we're talking about in terms of wave, and that's your flat. And here is your contact lines. And these are your dark bands. If we get the dark fringes, it's better because you can count faster, yeah, because it's giving you more color, so you can be able to count them easily. So the basic air wedge configuration comes from the surface inspection with optical flats, and we use gauge blocks with them. So the gauge blocks and the optical flats they rang together, okay, until the fringe pattern cross the block. So when you take a look at it here, we have 1, 2, 3, 4, 5 fringes, and they represent an air wedge, okay, with a height of 5, 1/2 wavelengths, okay, and they do not show which end is the open one. So that's how we count. So we already know the wavelength, so 1/2 of that wavelength, whichever wavelength that we use in the optical flat. So that's how we count the measurement. So the 5 fringes here indicate that there is an air wedge, okay, of 5 1/2 wavelengths height. This one, separating the flat from the gauge block. So if you do not see much change, you're pushing along the line of contact. Okay, then the end is right here in contact with the gauge block or part. So what this trying to tell you is if force, okay, here is your force, at one end doesn't change the fringe pattern, okay, meaning causes very little change here. That end is in contact with the gauge block or part, okay. Okay, when the fringes spread out, then the wedge is forced close, pushing against the open end. So here it shows height of the fringe, okay, represented by 5 parallel separation planes. So here what it's trying to tell you is when forced, okay, does widen the fringe bands. You know you are squeezing this air wedge close. Okay? You gotta understand they're very delicate, okay? So a little force is going to make changes on the pattern, okay, of the fringes. So if there's no change in the previous slide, okay, the end is in contact. And if there's a force, and you can see, okay, they spread out, meaning like instead of 5 fringes here, now I have 3. That means that the fringes, they spread out, okay? That's mean like you're pushing against the open ends here, yeah? So here on this side, these are again very greatly exaggerated. So just showing that the height of the wedge, okay, is represented by 5 parallel separation planes, this one, okay? And these are your parallel separation planes corresponding to these fringes. and each is going to equal to, again, 1/2, all right, wavelength. So the air wedge forms the basic configuration for fringe patterns, okay? And we can form just as useful fringe pattern if we orient the bands lengthwise, okay, along the block. Here is the block. And these are your 3 parallel separation planes right here. And these are your corresponding fringes right there. Okay, that come from our air wedge. So if the fringe bands had run lengthwise, the air wedge, okay, would still exist, and the contact could be found by apply force. Okay, I already show you to apply force right there. That can change the fringes or that doesn't. And don't think too much here. I just trying to tell you about the optical flat instrument and how we use the fringes, okay, and the wavelength to do the measurement, okay. And this is just trying to show you this separation, okay, and that separation, this is it's not existing one, okay. This is just like we're imagining these planes in our head, okay. Then they are anyway corresponding to the fringes in our instrument air wedge right in there. Okay, so now we get into relationships applied to the air wedge measurements. So we have 2 relationships here. So when the length is constant, okay, the fewer bands, and you will have a narrow angle. The more bands you have, the wider angle. So when you take a look at picture, you're gonna see the wide angle right there, many bands. You'll see a narrow angle right there, fewer bands. Now we're gonna make the number of bands constant, so you have 5, 5 on each side. Okay, and this is wrong. Okay, the bands are actually in this example constant, so get rid of that. So we have a short, okay, length right there, your x. See, so here the length is constant, so your x right here is equal to each other. So right here your x is smaller than this. Okay, so that's shorter, and then this is longer. So therefore, shorter the length, you have wide angle. Okay, the bands are numbers are the same. I think the author got it wrong here. And then your long length, okay, so right here, the length, the angle is narrow angle. Okay, when we have our bands, the number of bands is constant, the same thing. Okay, surface inspection. So in surface inspection, some part of the surface is arbitrarily picked, okay, as reference from which other parts are expressed. So if the fringe bands are straight and uniformly spaced, the surface is flat. Closed bands like this, okay, so when you look at it, they are not uniformly spaced. This is wide, and then here, right here, you have closed bands. So if you see like that with a big gap, okay, and then you've got closed bands after the gap, that means that you have a sharp drop off, okay, so which tells us the angle is larger along, okay, on edge than along the other. So here you have a one angle right there, and then you have a drop. See how the surface is straight and then the surface is dropped. So when you apply the light, this is what we see in our instrument. Okay, you're gonna see the first band here and second band here representing A. Okay, right here, this angle right there. So representing an angle right there. And then we have another set of bands, fringes right there, and they're equally spaced right here, okay, with the half wavelength. And you can see they're corresponding to these planes. So these are imaginary plane, okay, parallel separation planes. So meaning like the angle has changed to something else. And that's this topography right here, okay? So the surface drop. and we call that a sharp drop off. So here this sharp drop off is clearly shown by the closed bands, okay, on the right. Okay, here in this picture, we have A all the way to I here, okay? So the surface conditions can be detected, okay, by looking at the fringe patterns. So when you look at the fringe patterns, they're showing like the contour lines on the map. So here R indicates that's your reference, okay? So when you take a look at it here, these fringe patterns are all different, and they tell you about the surface conditions, okay? And here is one type that's a little bit curved, okay? Here you have a concave and convex. And here, different patterns. See how that goes? So these lines, the fringes, are showing how your surface is going, okay? So here we have a change right there, you can see. There's a change, it goes that way, and then another pattern coming in, okay? Here not so bad, only right here, okay? So reference meaning that's just our, your references were going this way. So here your references on this side, and here our references going that way. Here again in this air wedge, you can be able to say two different patterns. So you know that the surface is changing 1 time, 2 times, 3 times, yeah? The same thing here, surface changes 1 time, 2 times, and then 3 times here. Okay, so once surface conditions or configurations are recognized, and we recognize the surface condition by looking at the fringe patterns. The fringe reading fundamentals are formed, okay, from Wedge Method. So this is our Wedge Method table, and it's just showing you the fundamentals for your fringe reading. So it says in order to interpret the external band curvature from absolute straightness, it is necessary to know the reference line or point, okay, from which the measurements can be expressed. Imaginary lines parallel to the line of contact are expressed, so they should pass through the center of the bands. So even though the distance between bands varies, the height difference from band to band is always 0.00029 millimeter. So that's in inches is 0.0000116 inches. You can convert it, okay? You can use a conversion from Google. And it's always counted from the line of contact. And the third fundamental is the external curvature is always measured against the distance between the bands. So anyway, if you know a little bit, that's fine. Okay, so that's your fringe reading fundamentals by using our air wedge method. Okay, here is another one. So fringe reading fundamentals obey. Okay, these basic considerations apply to all optical flat measurements. So here in this picture, they're just the measurements. It's just showing you the measurements of the deviations, again, of bands compared with the distance, okay, between the bands. So when you take a look at it, you see all the measurements by looking at the fringe patterns, okay, and these measurements represented as, again, the deviations, okay, of bands compared with the distance between bands. So here we have your convex, okay. So that's your physics mirror, okay. Surfaces, we have different mirror. You have flat mirror, you have convex mirror, and you have concave mirror, okay. So here one band width is this much. So see this little arrow, that's our distance. And here a little arrow, that's 1/3. That's also 1/3 of this length, okay. So the same thing right here. So that's 1/3 That's okay, 1/2, that's 1 and 1/3. 1/4, 5/6, 1/2. So anyway, so we have these deviations, okay? And we're comparing the bands, okay, with the distance between them. This is low at edges because we have a two-layer, okay, contour right there, one here and one there, and then straight. These are ridges. This one is a progressively convex, and then here are straights. So two different patterns. Which way should the bands run? So fringe patterns show surface configuration. We have already studied that, and the bands are counted. We have already studied that to make measurement. Okay, so here these patterns shows different sets of bands to be counted, and we're gonna count from A all the way to C. Okay, the spacing of the bands depends again on the angle of your air wedge. Okay. So here in A, it shows the same pattern, okay? And in B is the same surface, but with a smaller angle. And C is a larger angle. No drop. And here there's sharp drop. And here also, okay? Well, because we have a big gap there and then followed by another, okay, set of fringe patterns. Here the same thing, big gap, and then followed by another. So we're seeing the surface configurations are different, okay, from here and here, here and here. So here you can see the relationship of two fringe patterns, okay, and the orientation A is reoriented into B. So here is vertical and that's a horizontal orientation. So in this orientation, you can be able to calculate the drop-off amount, okay, by using the fraction of one band. And here we represent the fraction of one band by x, okay, so like this. So you don't really have to go into details here. All you have to understand is we can reorient the surface. And if you do reorientation, you can use, okay, you can use the length of the band, okay, to calculate the drop-off amount, yeah, because the length of the band of your fringe totally corresponding to the surface configuration. So when the surface changes from one, okay, one pattern to another, so here you have a drop off right there, you can be able to calculate that amount by reorienting this way, okay. So both patterns, they show the surface conformation, but in B, it gives you the direct measurement of that drop-off. Parallelism. So parallelism of planes, we can measure it, okay, by using optical flats. So fringes are visible when the separation distance is very short, less than 2.54 micrometer or 0.0001 inches. So fringe conversion table, okay, and that's right here in figure 1629, and I'll show you. We're gonna use it as needed, okay? That's just for conversion. Okay, so the parallelism measurement with the optical flats is shown here in this picture. So that's your parallelism measurement. So parallelism on two planes is a measurement of their rotation about the x and y axis. So with gauge blocks, okay, a surface can always be constructed within the resolution range of optical flats. So here is our known part and here is our unknown part. This is our measure plane and that's our reference plane. So the problem is, what is parallelism of top and bottom surfaces? Separation too great for resolution of fringe bands, if we put this way. Okay, your measure plane and that's your reference plane, and here we're putting optical flat to measure this parallelism. Now we're going to add the known part. And that known part is very nearly same size as your unknown. This is what we're measuring. So substitute reference, and this is your reference plane, a surface to be measured, okay? And here is our optical flat. I'm going to put another one here and here. So we can be able to find this difference, and thus your separation small enough to permit the resolution. So these are fine measurements, so you won't make understanding out of it right now. It is we're trying to see, okay, if the surfaces are parallel to each other. And in order for us to be able to know the parallelism, we gotta use two optical flats. Okay, and we can use the unknown surface alone. We have to use a standard, and that's your gauge. And you put it there, and you put right here, okay? And when you put the part, you can be able to see this very, very small separation. And that's how we measure the parallelism. So if your separation is so big, your parallelism is not very great, yeah? If you have a very small, minute separation, then your parallelism is great, yeah? Okay, rotation. About the z-axis. And translation, so that's your movement along any axis, okay? Does not disturb the parallelism at all. So when we use a gauge block in parallelism measurements, a surface can always be constructed within the resolution range of optical flats. So here, it's just trying to tell you rotation about the z-axis. In translation, that's the movement along y or x. Okay, it's not going to disturb the parallelism measurement at all, so you can move. So therefore, to measure parallelism, rotation about both axes, okay, must be determined. So optical flats, that's our measuring instrument, can determine rotations simultaneously. We can do it at the same time. So we use a flat to measure the parts, okay? Then compare the fringe pattern to known block and your unknown block to measure the parallelism, yeah? Since we're using optical flats, we're using the lights, okay? So therefore you will definitely get the fringe pattern. You do it on the gauge, your known block, and then you do it on the unknown block, okay? Your part to be measured. And then you compare it. If the patterns are closely related or closely the same, then it's pretty good parallelism. If the patterns are kind of far away or have a lot of deviations, then your parallelism is not very good. Yeah. Okay, after the measurement, we check for parallelism. We check that one, the unknown surface is parallel longitudinally to the known surface because it produces the same number of bands. We're checking the fringes, okay? We're checking the bands. And if you get the same number of bands, we know that the unknown surface is parallel, okay, to the known surface. Now, the surfaces are parallel across the width because the bands on the unknown are at an angle to those on the known surface. So if you see the bands on the unknowns, okay, and they're at an angle to the known surface, we know that the surfaces are parallel across the width. And the unknown is out of parallel to the known by 1/2 band in one width. So these are all 3 points that we check for parallelism. So when you look at it here, both surfaces have the same number of bands, okay? They have the same number of bands. You can see right here, 1 all the way to 7 and 1 all the way to 7. But the bands on the unknown surface appear at an angle. So this is the band, okay? At an unknown surface, it appears at an angle. So here we have our known, and this is our unknown. Okay? So when you take a look at it, see this is our parallel lines and surfaces, and here, okay, isn't that parallel, okay, compared to the known. See, there's a little angle, so therefore you can see the band like that, yeah. So therefore the unknown is out of parallel to the known. So when you take a look at the band, you're going to see 1/2 band, okay, in one width, yeah. So simply put, it is trying to tell you the unknown parallelism is not very good. They're not very parallel to each other, yeah. Parallelism measurement can give information on these. So the relationship of planes in the x-axis, the relationship of the planes in the y-axis, and how much the planes are out of parallel. So this picture shows parallelism can exist on the x-axis, okay? More bands are seen on unknown here. That's your unknown, than on known, okay? So therefore, it's telling you the parallelism is on the x-axis. And here you can see 1, 2, and the 3. Only 3 bands. Here we have 1 all the way to 7 bands. So here, this is our unknown. And we have more bands on the unknown. And this is your known, okay? And you have fewer bands. In that case, we know that the parallelism can exist on the x-axis. Okay, so here in this picture, you can see the fringe pattern, okay, on y-axis. And we can know by looking at the numbers, yeah, so that's going to fewer bands right there. And that's more bands on the unknown, fewer bands on the known, so therefore they're out of phase. And here, in this case, you can see they're out of phase by 2 bands, because there's 5 here and there's 7 there, so the difference is 2. And here, in this case, you have your y-axis. Here, you can see the y and the x-axis. Okay, so parallelism is on both axes. Here is just for y-axis, because you don't see the angle right there, okay? In the previous picture, you see the angle, so that's for x-axis. And here is just straight lines, so therefore that's for y-axis. So here we have both, okay? Then here, that's our optical flat, trying to measure the parallelism, right? and this unknown. And that's our known that we're trying to measure. And these are very exaggerated, so it's not that big actually. So here in this picture, it shows it can exist, okay, in both axes at the same time. But surfaces can be out of parallelism in two axes simultaneously, okay? Meaning like we don't have to do it x and y one by one, like in this example. We can go both at the same time and measure parallelism, okay? But then it will be a little bit difficult for you to be able to read it. Here is relatively showing you, okay, that one is for x and then that one is for y. For theoretical learning, you just concentrate, okay, in the fringe pattern, and this needs a real instrument for us to be able to see inside. But just try to understand that we okay, look at the air wedge and the fringe pattern right there. Then for this, go y-axis, and if you have an angle right there, then you're gonna go with your x-axis. If you get it, okay, that's alright. Okay, now we come into applications of optical flat measurement. So here, optical flats are used in certain applications like ring seal inspection. Band pattern produced by rotating seal. Okay, that's not flat, and they have greatest variation from flatness cross around the center. So anyway, here if you get like application, we use it to in ring seal inspection, you're okay. So right here, it's just showing you the optical flats in square gauge block. So here is your square gauge block, and this little transparent one is your optical flat. Okay. And on this side, you can see we put it here. That's your micrometer, and that's your flat right there. Okay, so flatness check of the measuring phases, and we use the interference fringe pattern. That's pretty unique, huh? So special optical flats are used to examine surfaces inaccessible with standard ones. So we call these surfaces like really difficult to reach. So we have to use a special optical flats, not the regular one. So one here you can see the extra thick flat, okay, for a particular type of surface. And then we have flats with gripping, okay, so that's for surface B here. And we have chef, okay, passes through the flat, so that's for another type of surface that you can't reach. So anyway, we have different optical flats, and we use them in order to reach certain surfaces, okay? So a fringe conversion table, and that's in 1628, which is actually this one, okay? That's your conversion table. And this one is your figure 1629 that we talked about in the first few slides. And that's your metrological data for scaled instruments. So here in the conversion table, you can see these are your number of bands, then that's your metric nanometer, and then that's your micro inches, British, and then that's metric. Here on this side, you can see your instrument. Your measurement is direct, your range, your precision, discrimination, sensitivity, linearity, and your reliability. Okay, that's our standard table for metrological data. In this case, our optical flats. Interferometers used in physical sciences, we also use in industries. So the principle is the same as your optical flat measurement. They have greater stability and they use laser, okay, therefore greatly extend the potential range and discrimination. It's just another type of instruments using optics. Okay, that's it for part 1 of chapter 16. Chapter 16 is a big chapter, so you have 3 parts. Alright, we'll move on to part 2.